Good morning, everybody. So we have 17 responses. Did you guys do your pre-class homework?
Yeah.
Nah, I hear a mixed response and I see mixed results on the clickers. Come on, buddies. Okay, go ahead and click in then. I'm not worried about the number of clicks. I'm looking at the distribution of responses, which indicates that maybe they haven't been worked through. So let's take a minute and go ahead and work through this problem. Let's get running right away. If you came into class after I handed out exams, I do have the exam wrappers. And also if you're in, totally blanking on her name, Miss Douglas's lab, I have your Experiment 7 quiz. So make sure to grab those before you leave so you can use those to study for the lab final that you'll have next week. I do not have Sam's. Miss Douglas just dropped by yesterday and gave me those to give back to you. So let's go ahead. Is this a terrible idea to give you guys stuff back during class?
Yeah.
Josh, can you help me out? Just focus. Just focusing, that's all I'm asking. On class, yeah. We got pretty loud and excited today, which is great. Let's try to use that energy to focus on crushing. I'm trying to put together a whole bunch of different opportunities for you guys to look back and reflect on material we've done this semester so you can do even better on the final exam. This is something I've not had the luxury of doing in the past semesters, but we have here because there's a couple of things we usually do first semester Gen Chem at my previous institution that we don't do here. So it allows us to do some reflection and some, I guess, review if you want to call it that. So we'll be starting that today. So the more we can kind of get up and running, go through some logistics in the beginning, the more we can focus on that. So let's look at this problem here. So this is relating back to the question that we did at the beginning, at the end of last class. We were talking about biofuels. We want to take 250 liters of biofuel to get to the North Pole. We got a shipment of that biofuel in, and someone thinks it smells like gasoline. So we want to test it to make sure. That's one of the things combustion analysis is very useful for, is we can actually take a substance, we can do a combustion analysis of it based on how much CO2 and water come out. We can tell what the substance was that we put in. So why don't you go ahead and talk to your neighbor. We have a variety of answers. If you did complete it, talk to your neighbor, see if they used a similar approach to you, came to a similar conclusion. There are a couple of ways you can do this. So take 1 minute to discuss your approach with your neighbor, see if there's any differences, and then we'll use that to discuss this question going forward. Garrett was saying that his first one is the last page is just to say no, and then you try to get again to say the second time, sometimes that
I didn't get any of that because the difference between, or rather, if you add the stuff, it's correct. The difference is very small.
Let's see. There we go.
Yeah. I got 0.001.
All right. How did we work through this? Combustion analysis is one of the more challenging problems that we've done this semester because it requires you to conceptually think about conservation of mass, stoichiometry, dimensional analysis, and then proportions, empirical versus molecular formula, a whole bunch of different things. So how would we start this problem? Let's go through and work through it relatively quickly. Can I hear from different people how we come from how we do each component of it? Markeith, how did you start working through this problem? Oh. Okay. Okay. How do we go ahead and start it? Ruby?
Start it with the grams of CO2.
How many grams of CO2 do we have? Can you remind me?
6.16.
Okay, what do we do with that?
And then convert from the grams of CO2 to moles of CO2 using the molar mass.
So we convert from the number of, how much we have in grams, the weight of it, to the number of them we have in moles. Okay, and then what do we do next? Let's go ahead and kind of have everyone popcorn these types of answers. Go ahead and raise your hand. We'll do one at a time. If we know how many moles of CO2 we produce, Stripty, what would we do next?
Then you would convert from 1 mole of CO2 to 1 mole of carbon.
So every mole of CO2 contains 1 mole of carbon. Why is that important? Why do we care about the number of moles of carbon in the products? Okay, but that's in the reactants. So then how do we use this to think about, we're specifically finding the moles of carbon in the product. Can someone specify why we're looking for the moles of carbon in the product? Kiana? Okay, so if we look at our CO2 in the products, we want to know how much carbon is there, but the big question is why. Joey?
Is it so you can go back to the beginning of the reactants and see how much carbon was there so you can match them up?
So how does that relate? How does the amount of carbon in the reactants relate to the amount of carbon in the products?
What you start with is what you finish with.
So we have some sort of fuel. We don't know if there's oxygen or not in that. We added O2. And we generated CO2 and water.
It'll be easier to figure out which fuel you use because each fuel has different amounts of carbon.
Okay. And going back to kind of one of the first statements you said, that any carbon dioxide that we produce, we presume that all of that carbon came only from our fuel. So going back to what Tripty said, the one piece I would add to what you said is that the carbon in the products came from the reactants and only the reactants. So we can find the ratio if we know how much carbon we had in the products because that's the same as the reactants. Okay? So then, now we know how many moles of carbon we have. We can stop our calculations there if we want. Can someone tell me how many moles of carbon you found if you stopped the calculations at that point?
0.139.
Great. And one more calculation we might do with that. Ruby?
Grams.
So we might convert that to grams. How do we convert moles of carbon to grams of carbon? What if this was all carbon 12? Would that still be 12.011? That would be 12.00000000 grams. All right? So then how many grams of carbon, Josh?
1.68 grams.
Great. And then can someone else suggest what we would do for our second calculation? Josh, you want to continue?
2.84 grams of H2O. That's given in the problem. Over 1. We're going to continue with the molar mass of H2O is at 18.01528 grams. Over 1 or under 1 mole. Keep going.
Sure.
And then that's under 1 mole of H2O over 1 mole of hydrogen. Wouldn't it be 2 moles? Is it 2? Okay, so that's where
So how many moles? What is this sentence saying?
There's just one for every.
Shania, can you say it nice and clear?
There's only 1 mole of hydrogen for every H2O.
Okay, so for every molecule, we can say mole or molecule, whichever one, the ratio stays the same. Every H2O contains 1 hydrogen is what this sentence says right now. And so we know that's not completely accurate. We're going to change that. So there's 2 hydrogens in every H2O because we're trying to find how many H2Os were in the product. All right? And if we stop our calculations there, how many moles of hydrogen do we have in the product? Can I get a number from someone?
0.315.
Moles of H. And then if we wanted to find the mass of that hydrogen, what would we have as our conversion factor there?
1.008 grams of H over 1 mole of H.
Great. And that would give us the mass of hydrogen in the products, which is
0.3178 grams.
317. Okay. We have to go through these steps. All right. And the reason that I'm stopping at these 2 points, hopefully you guys are comfortable with that. We'll talk about that again in a second. We'll need that for the ratio. So what's the question we can answer right now?
Is it methyl oleate? Because methyl oleate would have oxygen, and this doesn't look like it has any oxygen.
Well, how do we know if it has oxygen or not? How do we use these numbers?
Because you have 2 grams of fuel, right? That's what you started out with.
Correct. We have 2 grams of fuel.
And you add those two together, and you get a number that is basically 2, within the margin of error, basically.
Okay, so with our sig figs, we can know with certainty to the hundredths place. And so if we know to the hundredths place, we add those 2 masses together, we're going to get 2.00 grams of CH. That means that we have no unaccounted for mass. That means that our product cannot contain oxygen, because if it does, it has 0 grams of oxygen. So right there, we can answer this question, we can be done. If we want to be completely certain, how do we know, how do we figure out the empirical formula?
You divide 0.135 moles of H by 0.1399 moles of C.
0. You mean 315?
Yeah,
By, what did you say?
0.1399 moles of C. And then moles of C divided by moles of C.
So what did you get for this ratio here? Anyone do that ratio? DeAndrea?
2.25.
I got 2.25, but then it broke down to 9.4.
Okay, so let's do carbon is going to be 1, and then we have H 2.25. Is that our empirical formula? Okay, we can't have a quarter of a hydrogen, but it's important to note that that's a quarter. So 2.25, how many times do we have to multiply that in order to get to a whole number? All right, then we have C4, H.
9.
That's our empirical formula. Does that match either one of the 2 reactants? Either methyl oleate or octane?
It doesn't match methyl oleate.
So then, you've had your one. Very strong already. All right, so then it's neither, right? We're done. Correct? Why? Okay, so those would be molecular formulas. So how does this empirical formula of C4H9, does it compare? Can we multiply it by any factor to get the molecular formula of either of those 2? Amber? So we need to be looking out for, we're always going to get just the lowest whole number ratio out of combustion analysis. Once we do that, we need to think about how does that lowest whole number ratio, the empirical formula, compare to any of the possible molecular formulas. We might have just been given the molar mass, and we'd have to see how many we multiplied the molar mass to get to the molecular weight.
So this is how, like, that's where I kind of got stuck, because we didn't have, like, a mass that we were given to, like, divide the empirical formula by to get the molecular. So you would just see if the numbers in your empirical formula could be multiplied to get any of the given moleculars.
Yeah, and so maybe what would make this problem a bit more challenging, actually, no, I think you have all the information you need, right? So you would have the ratio of all of these, and then here having the formula for octane. you would be able to look at the ratio of carbon to hydrogen. So it's either looking at what's the molar mass of the empirical formula. If I hadn't given you this, and I had just said that it has a molecular weight of, I don't know what it is off the top of my head. Anyone know what octane's molar mass is?
114.2309.
So if I'd given you the molar mass, what you would find is the empirical formula is exactly half of that weight. So then you could find that the multiple of 2 of the the empirical formula would give you a formula that has the molecular weight that we know it should be. Joey?
So what if you went about it a totally different way?
Okay, so how'd you go about it?
Start off with 2 grams of methyl, whatever.
Manu, do you mind closing that door for us, please?
2 grams of octane, converted all the way to CO2. Did the reactor, and then went all the way to CO2 and got.
Fantastic. That's why I said turn and talk to your neighbor. There's multiple ways to answer that. That is a fantastic way. Did everyone understand what you're saying?
No.
So can you explain it one more time?
So we started with, it says you start with 2 grams of fuel, so we started with 2 grams of methyl oleate or whatever, however you want to say it.
Yep.
And octane. We did a stoichiometric equation with that one, all the way up to CO2. Then it's 3.
So you'd have to balance the equation for the combustion of each one of those. And then you could say for every 1 mole of methyl oleate, we produce 19 moles of CO2, 1 mole of CO2,
44.
1 mole of carbon. Oh, you did the grams of, sorry.
Yeah.
And then you basically determine if we burned methyl oleate, how many grams of CO2 would be produced. Fantastic. Great way of working through that problem. Absolutely correct. It might take you a little bit longer. It might take you shorter. It depends on whatever you're more comfortable with. And you do the same thing then for octane. See how many grams of CO2 would be produced by burning 2 grams of octane. Fantastic. Is there another way you could do this? Dawson, you do it a different way?
No, I did that way.
Okay.
You could have just looked at the amount of water produced instead of CO2, but that's about it as far as I know.
Okay. Aaron, did you, before in class, I remember you telling me there's a different way that you did it.
Well, I did exactly what Jackson said. I looked for grams of water because I know all of the hydrogen has to come from the sample. So
Okay. Love?
It doesn't really need to be grams, you just do moles.
We could do moles, but then we need to convert the grams of CO2 produced back to moles and compare those. Yeah. And I think I've seen people do percent mass before. So that would be a similar approach, but you would say in octane, what's the percent mass that comes from carbon? What's the percent mass that comes from hydrogen? And then look at in our products, if you compare hydrogen to carbon, I think that we can look at that ratio as well. So there's a number of different ways, and any way you guys do that is totally fine. Any questions? This problem, I think, was easier than some because you have fewer elements, but it's harder than some because you have to assume that we don't know if there's oxygen, and you have to look for that if you do the approach that we did first. If you do the how much CO2 do we make, it negates that step and makes it a bit easier. All right? So let's go ahead and close that out. So I have some announcements. I did send out way too many announcements on Monday. I apologize. I hate doing that. I usually try to limit to 1 a day, but there are multiple things I thought of at different times that I should have held. If you are interested in the learning assistant peer mentoring kind of thing for this spring, there are multiple opportunities. I think we're going to have in-class assistants. So the way that Sam kind of walks around and asks you questions and guides you forward, we're going to have that as one of the possible ways to interact with students in the spring, as well as leading your own workshops that are going to be happening once a week. You'll be running 2 of them, so it's about a 4-hour commitment a week. The in-class assistant is probably going to be about a 2-hour commitment a week. So if you're interested in doing that, please complete that Google survey, the Google form that I sent out, one of those announcements. And we need those responses by Friday to get a feel for how many people are interested and then to go through a selection process after that. If you're thinking about doing it, not sure if you are eligible or whatnot, come talk to me after class, and I'll let you know how things work. Homework, just to clarify, pre-class quiz for today was what we just worked on. Some people worked on it, some people didn't. We have a pre-class quiz for Friday that's pretty short. We have homework for Sunday that's extremely short. I think it's 3 questions or 3 categories, mastering categories. I decided that I was going to load it up with all the review stuff, but then I didn't want that due on Sunday. I wanted you guys to get a chance to practice that before the exam. So I think that this one is technically due December 10th. I think. I would advise doing it before December 5th, which is our first final. I decided to give you guys 10 extra credit points if you complete it. So that is points to motivate you. What's that? It's one of the only extra credit things I've given you this semester. So hopefully you feel comfortable with that. It will go towards your homework category, and those 10 extra credit points will then just be added onto your homework category. Savannah?
I was going to ask if it was going towards the test.
10 points to the exam?
Why don't we
For practicing for the exam? Does that sound fair and reasonable? Okay, one of the other professors from the other classes comes in, and I tell them, I'm giving everyone 10 extra credit points in the final exam. I think that might bias the results of the exam. So I will not do
They
that.
have done that before.
Some people like to curve exams, and I don't like that either, because if everyone in this room gets 90% average on the exam, I'm not going to bring that average down to 70. That's what curving means. Okay? So curving is not what you guys want. I think I've heard a number of people say, please, can you curve the exams? Our averages have been above 70%, which means curving them would pull your points down, which no one wants.
How about dropping one of our bad grades?
So on the final exam, if you crush it, I will raise your grades on the previous exams, that if you scored lower on that particular concept. So there already is a way in which I'm allowing you to earn credit back, just like the exam wrappers. If you didn't do exam wrapper for 1, 2, well, obviously no one did it for 2, exam 1 or 3, your final exam score on those particular topics will influence your exam scores on your previous exams. So it really encourages you, if there's something you didn't master, go back and master it now. Come to one of the multiple exam review sessions that I posted about, work through those problems, work through them in other ways. Show me you can do it at the end of the semester. That's the most important thing, and then your exam scores for the other ones will go up. DeAndre? Exam 2, everyone will have the final exam score reflect on their previous exam score, and that will boost it for the questions that you didn't do well before.
Does that only count for the final that you write, or the...
That's, I will try to do it for both finals, yes. I will do it for both finals. It will be difficult, but I will do it. I will have other office hours between the 2 exams. I haven't figured out when those are yet, but if you send me an email reminder, I'll try to figure out when those are. Remember at the beginning of the class, we had a survey that everyone took that let me know where you guys have some strong background and where your background's not as strong and your identity as a scientist, those kinds of things. I am going to require that you do one again at the end of the class. It will count for a post-quiz. This will be your post-quiz for week 14. Okay, you don't have a post-quiz for week 14. It'll take about the same amount of time. I think it took 20 to 30 minutes on average to complete that survey. I really want you to do this, and I want you to be thoughtful in completing it. Don't just click through answers. There's actually a way I can tell if you do that. And so if you do that, I'll be tempted not to give you any credit for the post-quiz. So just answer the questions. They shouldn't take too long. They're not a lot of calculations. And it gives me a real amount of insight into how your mindset and your capabilities have changed over the course of the semester, which is something I very much value. I will send the link out today so that you can do that. You can complete it before December 10th. If you don't complete it by December 10th, or if you don't actually try to do it, if you just click through, then I will not give you credit for that. One of your quizzes will be a 0. Any other questions on these logistics, Kiana? You said when are the finals? So the finals are December 5th. Is our required, that's our scheduled final exam. It is 70. I went through and looked at all the material, which is what I've developed this next week's worth of curriculum off of. 70 multiple choice questions. It is designed to be completed in 110 minutes. We have 120 minutes for it. So it is a substantial exam. You need to make sure to pace yourself, but it is relatively conceptual. There's not as many calculations as you might expect in a chemistry exam. You are not allowed to use a graphing calculator or a note card on that exam.
No,
it does give you standard values, so like the speed of light, R value, those kinds of constants. There are 0 equations on it. So you will be expected to know the polyatomic ions we've been working with all semester. You will be expected to remember equations for the speed of light versus frequency and wavelength, those kinds of things. There are very few equations I think we use this semester. That might be the only one. All right, and then December 10th is the exam I will write. There are no other exams scheduled at that time. December 10th, 8 to 10 a.m., according to the university schedule. If you will be out of town or absolutely can't make that, send me an email, give me some other alternative times. I will try to have everyone who can't make that final exam take it at a separate time. All right, you can only take this if you have taken the ACS final exam. There is no way to only take this exam. You will not get credit for it. It is very similar in format to my other exams, a little more weighting on the last material because we haven't been tested on that yet. 120 minutes is how much time you have for it. I will bring my graphing calculators you can use. You cannot use your own. Because you can't use a graphing calculator here, I'd advise that when you're studying for the final, you practice with a non-graphing calculator. And you can bring a note card to my final exam. That was a question I was asked last class. Normal size. Standard note card with 3x5, I think. 3x5, same rules apply, no polyatomic acid, polyatomic ions, strong acids, and bases. All right, any other questions?
Do we need no acids and bases for the ACS, or is it not?
It probably will expect you to know the strong acids and bases, yes. There's only 6 strong acids, and then a strong base is anything with a hydroxide. So I think that's reasonable as far as memorization. All right. So what we're going to be spending some time on today is predicting the relative boiling points of pure substances. That's one of the last things that's somewhat new, but it's kind of related to what we've already been doing. And then the majority of the rest of the class and the rest of this week is going to be, and Monday, is applying concepts from the semester to new and older problems. So we did combustion analysis, categorizing bonds in larger molecules based on their shape, polarity, and other properties. And then we're going to be talking about going back and revisiting what does it mean to be a different element, a different isotope, what properties do they have, where do those properties come from, those kinds of things. And it looks like I did not animate this. So let's go ahead and answer the first question about methyl oleate. And you should have the structure on your worksheet. Send me a photo of this and then ask me about that in an email. I will double check that. So we're looking at the first question. How many sp2 hybridized atoms are in methyl oleate? You can go ahead and start answering the next couple of questions if you want, and I'll put those in a second. Something's a bit rusty. A little rusty. Yeah. All right. All right, if you're stuck, please raise your hand, ask for a little assistance, or check with your neighbor.
I think
I go.
oh, you go ahead.
No, you can go. You can go. I completely forgot this.
I think the ACH test, and then surely that the first wrapper and the third wrapper that I missed it is input over there, and then I can.
So whichever of the finals you do better on, those will count towards your other team.
What I mean is, yeah, I know. I'm sorry. What I mean is, wrapper 1 and wrapper 3, I cannot satisfy. It's not
Correct.
yes. So when in ACH there is the
Same topic.
Yeah, the same topics. If I'm right there, are you going to?
So let's talk about that after class.
Oh.
I just completely forgot. I mean, it says SP3, right? So SP2. I'm sorry, SP2. So if we go on the periodic table under SP2, we have carbon.
It's on the periodic table? All right. I see that you guys might have some review to do of hybridization and atomic orbitals and molecular atomic orbitals as it feeds into hybridization. So what does sp2 hybridized mean? Kayla?
It's trigonal planar.
Great. It means it's trigonal planar because it has what's the steric number of anything? It's sp2 hybridized. It's 3. So remember, in order to have, so if we have a carbon, for instance, that's sp2 hybridized, it means out of the 4 valence, out of the 4
Potential bonds.
atomic orbitals, so carbon has 2s, 2p. We have an excited carbon. We want to form a steric number of 3. We hybridize 3 of these. We end up generating sp2. We have 3 of those, each with 1 electron. We have a p, 2p left over. So we're looking for something with a steric number of 3 that has 3 identical orbitals, a steric number that reflects that. So where in this molecule do we have steric number of 3? Sarah, do you want to circle one? Okay, so carbon always has 4 bonds, so when we see carbon with a double bond, with 1 double bond, we know that it has to have 2 others. So each of these 2 carbons in the middle of methyl oleate have a hydrogen that's not shown. That means each have a steric number of 3. Same with this carbon here, steric number of 3. Are there any that we might have missed?
The methyl group.
So the methyl group is a CH3 attached to the oxygen. So it's a steric number of 4.
Maybe the oxygen. I'm not 100% certain on that. But
What's
maybe.
the steric number of the oxygen? What's missing? What's not drawn?
Lone pairs.
How many?
2.
What's the steric number of that oxygen? 3. Okay, so there are 4 sp2 hybridized atoms in this molecule because they have a steric number of 3.
I originally put 4, and then I doubted myself about the oxygen, and then I put 3. So dumb.
All right, so then I want you to determine how many sigma bonds are in this molecule. I will give you exactly 1 minute. You should be able to identify how many sp3 and sp hybridized atoms there are in the molecule too. We're not going to go through that.
What?
30 seconds. All right, and we're almost out of time. So what's the thing that's taking a little bit of time?
You just have to count them.
We have to draw in a whole bunch of hydrogens or go through and remember how many hydrogens are there. How many hydrogens are at the end of this tail?
3.
There's 3, so that means there's 3 sigma bonds, 1 to each of those, 1 to carbon-carbon. How many hydrogens are at this carbon?
2.
2 there. Okay, so we could do that all the way down the line. So if we do that all the way through, looks like we have a whole bunch of different answers. All right, I should have gone through and done this on my own. First, so I know that we have a minimum of, is it 36 hydrogens, right? Is the formula, is that right? What's the formula for methyl oleate?
C19H36O2.
I think I have it on the first slide, maybe?
Whoa.
All right, so if we look back at the formula, every hydrogen has a sigma bond, so there's 36 right there. And that doesn't count any of the other atoms that are connected to each other. All right, so then if we go, it's C18, 19, you're right.
I can do that, man.
Skills. All right, so we have 18, 30, sorry, we said 36 from hydrogen for CH bonds. What about carbon-carbon bonds? 1, 2, 3, 4, 5, 6, 7, 8. What about this one?
It's this one.
9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then, are there any others we didn't count?
No, I was so close.
Did I miss any? Did I mess up that math? So the one thing that you might have been confused about is that where we have a double bond, if you had thought that's only a pi bond, you would have been wrong. That it has a sigma bond and a pi bond, that's going to be really important to keep in mind. All right, and then our next question, how many pi bonds are in this molecule? I'll give you 15 seconds to click that in. How many pi bonds are in this molecule? Say again?
I was just trying to get the connect. So
And closing. Can you circle the pi bonds?
oh no.
Just 2? All right, we only have 2 pi bonds in this molecule. Each which have a sigma bond underneath them. Okay? How do you guys feel about identifying sigma and pi bonds? Sounds like you might need to shake the cobwebs off of hybridization and some molecular shape stuff. Let's check out molecular shape. So click in a number for which answer you agree most with. This is numeric answer. What is the electron pair geometry at that particular atom? What atom am I pointing at? Carbon. All right, a couple more seconds. All right, closing out. All right, so we have a majority of answers being split between these two, between it being trigonal pyramidal and trigonal planar. What's the steric number around that carbon? 3, there's a hydrogen there. If we have a steric number of 3, it means it has to be trigonal planar. All 3 of those. Trigonal pyramidal, when do we get that? What's a steric number for trigonal pyramidal? 4, where one of them is a lone pair.
We don't have any lone pairs here.
So there's no lone pairs. It cannot be that. All right, what about this guy? 15 or 20 seconds.
Let's just keep reconnecting. I'm going to lose issues. It takes so long to do that, too.
All right, closing out.
Seriously lost answers because of that.
Whoa, whoa. All right, 82% say it is 5. 5 is tetrahedral. What's missing in this drawing? 2 hydrogens, because carbon has 4 bonds. We're only showing 2. So that means that's a steric number of 4. All of them are bonding, so that's going to be tetrahedral.
I don't think carbon can have lone pairs.
It can. It's called a carbene. It's crazy. Sorry, that wasn't supposed to be laughable. It's just an unusual thing you don't learn about in Gen Chem. So it's something that we'll learn about in Orgo. No, not at all. But it exists, and we use it in organic chemistry to do very specific reactions. It is very hard to form, very unstable. All right, last one. I think last one. What's the electron pair geometry on that atom? Go ahead, quick it in.
Okay, so not in stable molecules, but like in
so
certain radical reactions?
So it's not a radical, it has a lone. So radical means 1 electron, so it's the 2 electrons.
Okay.
And it means that you rip a hydrogen off, a proton off, and leave behind a lone pair. It's a way to form carbon-carbon bonds. Spend a little bit of time Google on it. It's pretty cool.
Okay.
All right, closing out.
Nice.
72% think that it is, what are we at? 4? Trigonal planar. Once again, steric number. It's 3. There's 2 carbon-carbon single bonds. Well, carbon single bond, carbon-oxygen single bond, and carbon-oxygen double bond. And last one, electron pair geometry. A couple more seconds. Remember, we're talking electron pair geometry, not molecular shape. But go ahead and write down the molecular shape for all the ones we've been looking at. A couple more seconds. And we are closing out. All right, almost everyone is saying 5. But that doesn't look tetrahedral.
You forgot about lone pairs.
All right, so with every time we look at a big molecule, we have to think about, are there lone pairs or hydrogens that are not drawn? Because there's 2 lone pairs, the steric number is 4. Steric number of 4 means that we have a tetrahedral electron pair geometry. What about molecular shape? What's the molecular shape around that oxygen? Bent, right? That's where the atoms end up in a tetrahedral electron pair geometry. They are bent compared to each other. What about the other ones? What about this guy right here? Still trigonal planar, not any different electron pair geometry and molecular shape because there's no lone pairs. What about our other 2 sites? Are there any lone pairs of those 2? Nope. That means that our electron pair geometry and molecular shape are the same. All right, so we're not going to go through each one of those for molecular shape. But how many of those atoms with arrows pointing at them are involved in a polar bond? Is it just one of those atoms? Is it 2 of them? Milner.
Yeah. Sure. Multiple jobs. Oh. Soccer job.
All right. Closing out. So what do we have to have in order to have a polar bond?
Unsymmetrical?
Unsymmetric in which way?
Molecular shape.
Okay. Yes. So if it's symmetric, depends on what's attached. What's the first thing we have to say if there's a polar bond, though? So we're talking about bonds here, not overall net dipole. What is it we're looking for? Great. We look at what it's bonded to and what the relative electronegativity values are. So we have a carbon bonded to an oxygen, carbon bonded to another oxygen. Those both have differences in electronegativity, means those are both polar bonds. Oxygen connected to a carbon connected to a carbon. Those are both polar bonds. Over here, we have carbon connected to carbon, and what else? Two hydrogens. All of those are very similar electronegativities, so those are not polar bonds. If we see an oxygen, does that mean that there's a polar bond there? Have to be really careful. There's examples where oxygen is bonded to itself. O2, ozone. An oxygen does not mean there's polarity. An oxygen bonded to almost any other element means it is very likely a polar bond.
What about fluorine?
That is still a polar bond. So I had a quicker question for that. Go ahead and modify this statement to make it true. I think you have this written down on your worksheet, right? Question number 8. Modify that statement to make it true. There are 2 of the question was how many of these are involved in polar bonds, and 2 of them are involved in polar bonds. How many total polar bonds in the molecule? That's a different question. That would be 3. All right, so what is the modified version of this statement that would make it true? There might be multiple things you could do.
You can say most of the time you see an oxygen, it means there's a polar bond, unless it's, like you said, bond too. So.
Great. Most of the time, when we see an oxygen in a molecule, it's part of a polar bond. And then the little caveat at the end, unless it's bonded to itself. That's fair. All right, there's a number of different ways that we could say that. Let's leave us with this thought here, because your homework is related to this, your pre-class quiz for Friday. We're looking at a lot of molecules with the same molar mass. Would you expect the boiling point to be very similar? So what other factors? What factors might we need to consider in addition to weight? So specific heat is about changing the temperature of it, not necessarily about the temperature at which it boils. What's that? Not quite. I can't think of how density would fit, but maybe it does. Eric? The structure.
What about bond?
Say again?
Bond weight?
So there's a lot of ways in which it might show itself, but here are 5 different molecules that are all about the same molar mass, and look at their relative boiling points. It's a huge difference.
Pretty big difference.
What's the huge difference? What's the big difference between all these molecules? It's not the weight of them. The number of So nonpolar bonds compared to polar bonds. The more polar molecule it is, the more likely it is to stick together to its other molecules, which means it's harder to become a gas and overcome those interactions. Your pre-class quiz on Friday involves how much heat is required to get those molecules moving past each other as a liquid and moving much faster past each other to become a gas. So keep that in mind. There's going to be 1 or 2 questions pre-class quiz. Also go back to the announcement and make sure you look at the specific times where we have exam review sessions. There's one tomorrow, Friday, and Monday.
So